out in the control field. And this camera's not as big as my other one. Oh wait, let's go to control. I can't make it bigger, but I can zoom a little bit. This is a relay, and you can really see it on this guy. This is called what we call a latching relay. We'll run into a lot of these, especially crane control that's got a magnet on there. Cranes, electric cranes or radio controlled cranes will lose. We call it lose the reset. And the problem is if it loses the reset and you're using a relay to pick up, turn a crank to turn on a magnet on, what's going to happen? Yeah, it could actually drop the load. So we have special little relays we call latching relays. I like this little tiny one because it shows you basically how it operates. So let me turn on the. So the way they do that is that a latching relay has two coils. And these guys are used so often that there's even latching relays. One of your options when you set up a PLC is one of the relays you can bring in is a latching relay. So this is a little latching relay right here. So notice it has how many coils? 2 coils. And what we have to do to, I don't know if I can make it swap or not. It looks like somebody's dropped it. But what we do is one of them would cause the relay to come in. It falls into this little old tiny groove right here on this. Huh? There's no signal. Oh, I know what's happening. No. Sometimes this gets pulled out. Of course, this. So can you see the little latching mechanism right here? Yeah. So what we do is we pull in one and it'll latch the contacts, and if power fails, now what happens? They stay there. And to come in and make it drop unlatched, then we have to pull in an unlatched coil. So these guys here are for safety reasons. So if you need to have something stay energized, even when something happens, then we use what we call a latching relay. This is its big cousin right here. And so here's one set of coils right here. And the other one is actually right up here at the top. So one of them is going to be what? Latch. And one of them is going to be unlatched. In fact, the thing is latched right now. I don't know if it's got an override or not, because the armature is pulled up. Can you see the armature right here, or the plunger? So it's latched right now. And I don't know if it's got an override on it where you can unlatch it or not. I don't see anything right now. But it's got 2 coils in it. One would be to latch it, and the other one would be to unlatch it. It looks like the little one has been bent up, but you can actually see how it operates. This is a rotor off a single-phase motor, and I want to show you all the centrifugal switch that's on these motors. So this is the centrifugal switch right here. So it's got these 2 weights, and then it's got this slide pad right here. So what happens when it's spinning, it raises this guy here up and kicks out your the switch for your start winding is stationary. It's mounted on the frame of the motor. And so this would be a set of, and they're pretty common this would be the centrifugal switch that kicks out the start winding when the motor starts up. It's not when it comes up to speed. Y'all heard that thing click? As soon as that motor starts, usually they do what? They kick out that start one. And normally when we deal with commercial or industrial type relay coils, what they do is they encapsulate the coil inside plastic. And why do they do that? So this is a relay. Because it's made out of that magnetic wire. That magnetic wire almost has no insulation on it at all, right? You understand? In industry, these guys have to be really, really rugged. So normally what they do is but they're still replaceable. So this is a relay coil. So if your coil goes out on the relay, normally you got some pins or screws where you can drop the armature out of it and then replace. So that's the only thing really that's holding in there is just the armature, and then pull the armature out and replace the coil in there. So this is very popular in industrial relays. So
What is that again?
This is the coil.
It's just a coil? Okay.
The coil for the armature. For the solenoid that actuates it. So, so normally they have pins in them. This guy here we'd probably have to take out to pull out the armature. So here's that coil right here. That's it at the coil. And of course we have that. And then we have this residential relay. And you can actually see the coil inside your little control relay too. So remember, the control relay is inside the plastic covered unit. So this is a relay that came out of a residential situation. Or it came out of an air conditioner, but it did. And there's the coil right there. Well, we got that thing exposed, so if I drop anything on this or actually scratch it, then I screw that coil up, right? Because I scratched the insulation off of it. And if you scratch the insulation off and two wires come together, then you change the opposition of the coil, which means the coil is going to start getting hotter, and this is going to start causing problems. So what we do on industrial type relays is the coils are not exposed; they're actually encapsulated inside plastic. Right, they're still replaceable, but you have to disassemble it. This is a little harder because of the way the coil is mounted into things. So here we'd have to take the actual armature out, but notice it's screwed in. So it would be a lot easier to replace the coil than to replace the relay. Because if I can replace the coil, then I won't have to rewire everything, right? Y'all understand? So I wanted to show y'all that too. So timers, what are timers going to do for us? Well, there's a lot of things that, so, you know, I can get out of my car. I can leave my lights on. I can get out of my car, and once I turn the ignition off and close the door, my lights do what? They stay on for a little while and then they go off. So there's a timer involved there. When my blower on my heater runs, when the flame cuts off, it still blows a little while, right? You understand, to cool the firebox down. What's doing that? A timer. We stagger start motors a lot. Where we start one motor and then we start another one, so we don't have to. So we can fuse them with the same set of fuses, right? You understand? But they don't have the start current. So the start current, if you try to start a lot of motors at the same time. And one of the labs that we did, that we would do, was we had two motors, and we would start them with a timer. And every once in a while they'd screw up and blow the fuses in the disconnect, and those are 10-amp fuses up there, because they tried to do what? start two motors, not under load, so we know that those suckers were pulling over 10 amps, trying to start the two motors at the same time. Now, what we started doing is not hooking up the motors, but still put the magnetic motor starters in there. And that way, if they screw up with their timers, then we won't blow fuses. But if you understand a motor starter and you've already hooked up motors and stuff to it, then you have no problem. Sometimes we want things to run after. Sometimes we want a time after the fact, or sometimes we want a time before the fact, right? So when my heater comes on, they turn on a little purge fan and leave it on to purge out the box, right? To understand, they sense if it's on, and then after a while they'll actually dump the gas into the box and ignite it. That way, I'm not igniting residual gas that might be inside my chamber. So we have 4 major categories of timers. We have dash pot timers, we have synchronous timers, we have solid state timers, and we have programmable timers. So the timers that we put inside a PLC would be considered to be a programmable timer. So dash pot, synchronous, solid state, and programmable. The one that we'll be using is a solid state timer, which is pretty neat. So a dash pot timer kind of works like a bicycle pump. So if you got a bicycle pump and you cut the hose off of it, and you pull up your plunger and let it go, it'll just fall straight down. But if you come in there and you meter the outlet, so if you take your finger and put it across where the air is trying to get out, and you pull it up and let it down, then you can slow that thing down, right? And how fast it goes depends on how much of an orifice you make for that air to escape. Now we could use air or we could use liquid, right? Understand that. So this is what a dash pot timer works on. So we got a spring. We're going to use a solenoid to push a plunger in or let a plunger out. And then there's going to be a spring in there, a calibrated spring that we can control the tension. And we can control this. So we got a little adjustment that we can control the size of the orifice. We're moving between the two chambers. If we can control the speed of when you move between the two chambers, we can actually control the speed of the plunger. Now, we're not controlling the speed of the solenoid, or that's pulling in our plungers. What we're doing is controlling the speed of the timer. So this is a dash pot timer. A lot of them use these little electronic duty contacts. So where's my camera at? Yeah, but okay. So what we're looking at is, and it's locked up. I don't know why it does that. My other camera have no problem with it at all. And now I can't make it do it. I can't even close it out. So in Dali, I can't pause that. So we got all types. So we got 2 types of dash pot timers, or 2 types of timers. So we got quite a few categories. Within those categories, we have what we call on-delay timers and off-delay timers. This is a synchronous timer. What it does is real nice in that. So basically on a dash pot timer, it's hit and miss. So basically if you want 2 seconds, then what do? You get your stopwatch. That's what you do. And you force it in, or you cause it to energize, and you go stopwatch, and you time how long it takes. Okay, does that make sense? So another one we got is we have timers that's got a little synchronous motor on it. What's a synchronous motor? So an induction motor never ever runs at the speed of the field. A synchronous motor uses what we call, normally it uses a permanent magnet or an electromagnet as the rotor, as the rotating field. And a magnet will lock into the field because we're not inducing that magnet into the rotor. The magnet is already there, right? You understand? So a synchronous motor runs at field speed. And if it runs at field speed, there is no slip. So a synchronous motor has no slip unless you really load it down. That means I can calculate gear ratios. I can do everything to get exact speeds so I can make a thing run at exact speed that I want to. So the big difference here is that a synchronous timer, this is the synchronous timer right here. This guy right here has and it's called a synchronous timer because it has a synchronous motor. If it has a synchronous motor, then we can come up here and we can literally set a time on the dial on the front. But the coil is not a coil, now it's a motor. So when I energize this guy, I'm turning a motor on. That makes sense?
Is that like the old timers on a old oven?
Oh yeah, they had a timer on it.
You tell me.
Yeah, if it gave you a precise time, then normally that, or it could have been a ratchet spring, kind of like a clockwork. So if you heard it clicking, then that was done mechanically, and that was pretty accurate too. If you didn't hear it clicking, then of course it was probably a synchronous motor.
So the synchronous mode, you use that for like heavy duty stuff.
No, we just use it so we don't have to guesstimate at the time.
The reason I asked why you put it.
Well, it depends on what does the size of a relay determine? Well, it determines what it could run out. This guy's got to have a motor in it. So as soon as I say motor, you're going to start talking about size, right? This guy's got 4 sets of contacts in it. So they're single pole, double throw. So it's 4 pole, double throw contacts. So the contacts are going to be bigger. Normally you can feel this guy's got a lot of weight, and it's normally because of the motor. It's not because of the contacts, it's because of the what? The motor. So yeah, these guys are a lot bigger, but it doesn't mean that it'll pull more, it'll draw more current, or be able to control more current. But all your devices are going to be rated in when we rate contacts, how are contacts rated? What's that? Voltage in amps. It's just like fuses. Fuses are rated in voltage in amps. This guy doesn't give us a voltage on it, so odds are we would have to try to look this thing up. This guy's pretty old, but they're still out there. When you get out into industry, especially industry that starts out, that's been out there for years, and then they modernize as they go along, you're going to run into extremely old stuff, and you're going to run into extremely new stuff. So these guys are all over the place. They are literally all over the place. Oh yeah, I guess, and a company normally does not come in and change something that's doing its job. They don't go in and say, well, let's just go to the new stuff, right?
Saves money.
Saves a ton of money, because modernization is going to cost you a lot more than the original installation. Okay, then we have solid state timer. These are electronically controlled. These guys are really accurate. And normally when you get into timers now, they're either going to be PLCs or they're going to be solid state timers. So on this one, these are two. This guy here is that, so you can actually look inside of it. This guy's actually got a relay in it, which having a relay in it's nice because that means your contacts don't have to be DC and they don't have to be AC, right? You understand that? If it's a lot of solid state devices, you can't change that over. So if you get a PLC, it's either going to have AC output or it's going to have DC outputs or it's gonna have relay outputs. Of course, now preferred method is to get relay, because if you got a DC output module, you cannot output AC to it. If you got an AC output module, then the only thing you'll get out of the thing is what? Is AC, because they're using solid state devices to pass the AC and pass the DC. It's kind of like our solid state limit switch they're putting. The thing has a triac output. You don't hear it click. I mean, you go up there and you put a piece of metal in and it activates, so you don't hear it click. But the problem is that I could not pass DC through that thing, right? You understand? If it's got an AC, it's got a coil in there. With the solid state device might be a DC device or it might be an AC device. Then, so and we could have it pass whichever one we want it to pass. So, you know, these guys are usually set into a socket. So you wire the socket up, and then if something goes wrong, you don't have to rewire it like you would a relay. You just do what? You just unplug these things in and plug them back in. I'm not going to pass this around yet. This is programmable. So these guys have been around quite a while, so you might run into a bunch of these. Of course, these guys are usually considered to be unrepairable. Let me mess up or they get that stuff wrong, you just do what? Yeah, toss them. Now, a programmable timer, and like I said, I can't put my camera on. Or I could do this integrity. That might be what I need to do. That way I don't have to worry about it. What I'm going to do is I'm going to do this a part 1, part 2, and I'll upload